Okay, so assuming that you have a load, okay, so this is your voltage of the load, I mean the point of common coupling, and then your load is non-linear load. This is the I load, and this is the I grid, and this is the I DG. Okay? So your load is non-linear. You see that it's such a ugly, it is a reactive, harmonic, active, harmonic, everything that a nasty load can actually ask from the grid. Okay? So it's a very, very bad types of the load that we actually get lots of damage from it to our distribution grid. So, but this is a load, so it should work, and we need this one to get from the grid. And you see that all the current we need for the load is injected by the grid. But the problem is that the owner of the load will get a big bills for this type of reactive and harmonic which created by this load. So then he asked about the Rakesh, that Mr. Rakesh, you are a very intelligent man and you are going to actually design a system to solve my problem. And Rakesh said that yes, I can design a DG for you. So we design a DG, and this DG is connected to the grid, and by this you see that at 0.1 DG is connected. Before that, current of the DG is 0, so it doesn't provide any current, but in 0.1 DG is connected. We see that all the reactive, active, harmonic, anything that load needs is injected by the DG to the grid, and you see that grid is also very happy because they have all the required current. Sorry, load, I'm saying. Load is actually very happy because we have everything. So then it goes up to 0.2. So what is happening? Then we try to have another load and we add it. And we see that, you know, the DG also increase the current. We see that, you know, this harmonic, reactive, everything increased. But in our system, we mentioned that inject all the reactive power in fundamental and harmonic frequency plus the harmonic. And if we have extra, we can get from the fundamental frequency active power. Otherwise, we can buy. So it injects all the reactive power. All the reactive power in fundamental and harmonic frequency. And also all the active power in fundamental frequency and some part of active power, but the converter cannot inject more. So it means that the load demand is more than the power that we can supply by the DG. So for this case, rest of the power, which is the active power in fundamental frequency, is coming from grid. So it means that the grid can just provide the active power in fundamental frequency. Rest of the pollution and actually reactive, harmonic, and some part of the active power is injected by DG. So, did you get it? So now I'm getting back to Rakesh. So why we have this fundamental frequency here? Why we are not getting from this, from DG? Rakesh, do you want to buy ice cream for all? Yes? If no, please think, concentrate, and then give me the answer. Okay? So think, relax, actually, okay, don't listen to other people, and give them. Rakesh, I'm talking with, you're talking with him? Okay. If he answered It's fine. Okay, give me answer on behalf of Rakesh. If your answer is wrong, together buy the ice cream, okay? You can decide. You have also this, you are free to say no easily. So, tell me. Active power. But why not? We are not going to inject by DG. Is it correct? Yes? It's pity that we have actually camera. Otherwise, I said that next time you should bring this wooden. Okay? Sorry, I'm joking. Yeah, we have a document that he's threatening the student. Yeah, okay. So Rakesh, you decide. You want to buy ice cream? I give another chance. Think about why that current is not supplied by the DG. Limitation in which power is not enough to supply all the loads. So why we cannot actually supply that part? Yes. Yes, correct. Power is not enough. Power is not enough. No, he really wants to buy. I'm trying to say no, but okay, I'm joking. So, now get back to this load. So, load is ILD in fundamental plus ILD in harmonic. ILQ in fundamental plus ILQ in harmonic. Okay? So, by this ILQ reference, putting this one, we compensate all the reactive power in both fundamental frequency and harmonic. So if we get back to simulation, you see that our reference current in Q axis is all ILQ. Okay? But for the ILD, we see that all the ILD in harmonic is considered here. Okay? And some part of active power in fundamental frequency is also covered. Okay? When we increase the load, we see that it increased, this one increased, this one increased. But this is the maximum power we can supply. So this one and this one is supplied, and some part of actually active power is supplied, but then the rest is not, because it's a fundamental frequency in active power in fundamental frequency is not supplied. And the reason is that the maximum power we provide by converter is less than the power that we need for the load. So for this reason, the generated power is not enough to compensate all the load. So rest of the power, which is fundamental frequency of active power, is compensated by grid. So it doesn't provide any problem for the grid. So the grid, just you pay for the normal bill. Did you get the point? You're engineer, you should think like an engineer, okay? You said, okay, I don't know, this is because of the, what if we put the reactive? No. the reason is that we don't have enough power to compensate all the power of the load demand. So we inject maximum reactive power and harmonic, but if we have some available, it's like your load is 22, which 5 is harmonic in D axis, 5 is harmonic in Q axis, 5 is reactive power, and 7 is active power. But your converter just can provide 20. After some time, you see that it's a steady state. Okay? So it's because of this filter and PI controller. PI controller is not too fast. Forget that filter, and if you don't tune your Ka I and Ka P, later you see that this will be longer and then it's not good. So as much as your PI controller or your controller react faster, this transient time will be, look, we are from 0 to 2 and up to 0.022. Still we don't have too much power here because we are passing the transient time. And this transient time is the reaction of the PI controller. So it means that PI controller do like this one, and it takes from 0.2 up to 0.22. That time we had the transient time, and then we steady state, we see that, you know, it's supported. So then we see that, you know, all the active and reactive power in harmonic frequency and also reactive power in fundamental frequency plus part of the active power in fundamental frequency is compensated here, and then rest of the body, this red color, rest of the power is coming from the what is your name? Arshida. One time more. Darshita. Darshita. What is that red color? You can laugh also now. When you don't say something, she says, Darshita, tell. What is that? Great current. Great current, excellent. Yeah, we have actually this grid current here. So you see that grid current is sinusoidal. Okay? Grid current is sinusoidal. And one other important thing is that when you go here, you see that grid current is in phase with the voltage. Look at, this is the voltage, this is the current. And the voltage and current are in phase. What is the meaning of in phase? What? Yeah. So it means that the power factor of the grid is unit. So it means that grid doesn't provide any reactive power. Okay? So it is one benefit of this technology. So we get back again here. Darshita, yeah? Darshita. Okay. Okay. So Darshita, it's a grid, yeah? So what is, why it's here also? So you see that, you know, the load current is also reducing, but still we have grid current. So why this is when, okay. You want my help? No, I'm okay. You need my help, tell me. I take. Okay, go. So, Udaya, you see? Yeah. So, what is the reason? Delay because of the PI controller. Tell her. Yeah, exactly. We have actually PI controller. It has. Okay, so at least later someone asks you, you remember me. Oh, okay, it was because of the PI controller. Yeah. So I had a PhD. I was the actually examiner for a like a mid-exam of the PhD student, and the PhD student hears something about the switching state function. Then any question that we ask, he says, it is because of the switching. Okay. So you also react like this. It's a PI controller. Yeah. If you see PI controller, for sure, in any actually interview, if you notice something is wrong, and they ask, okay, why we have this problem? You say, probably PI controller is not working well. Then, like in 90% of the time, this is correct. Okay? Yeah. So, it is my tip to you. If you go to some interview, yeah, you see the PI okay, so no, then you, and then you see that, okay, yeah, okay, so what should we do? Probably we can control a little bit, tune the copy, something like this, and then they feel that you know everything, okay? Then after they hire you, they understand that. But when I start the interview with Aalto University, head of our department said that, so we had 2 days interview. Then he said that, okay, my last question is that what is your weakness? So I said that, I'm here to present the positive part of my career. When you give me the objective after 3 months, 4 months, you will easily understand what is my weakness. And he laughed too much and said, yeah, this is good answer, okay? So you should be politician, okay? Then later they understand that, what a big hat is in their head. Okay. Anyway, good. Darshit, I'm joking with you, okay? Don't cry, and if you say, okay, she said, then okay, good. Yeah. So, any questions so far? So when we look at this figure, then if you are like a doctor of the electrical engineer in the medical school, in electrical school, then when you look at this one, I easily can say, okay, the problem of this graph is that, okay, it has some delay. It seems that the PI controller is working, but not very well. So in the sensitive actually situation is not very good. So it can, and then the capacity of the DG source not enough to provide the power for all loads, but it's tuned well because we see that it has just the fundamental frequency. We can easily see that the voltage and current are in phase. In fact, the power factor of the grid is good. So then it seems that you have lots of information now by just looking at some figure. Okay, so this is what we expecting from the intelligent student. Then if they are analyzing some result, they see what is the problem of that and what kind of solution can be provided for that. So this is also power actually sharing between the grid, converter, and load. So we see that the active power and reactive power, we see that at 0.1 DG is connected. You see the blue color is DG is connected, and follow the maximum actually load power. So this is load, and we see that it follow the load. But when load increase, we see that DG can actually increase, somehow inject the same power because we have the limiter for that one. And then rest of the power is coming from the grid. Yeah, this is the grid. You see that this plus this is equal to this. But in the reactive power, we see that we are compensating all the reactive power when we have one load and two loads. So the power factor is somehow unit value, and it means that we could compensate the reactive power properly, harmonic, and part of the active power. And rest of the active power, which is fundamental frequency, is coming from the grid. One probably interesting question. Why this is very smooth, but here we have fluctuation here? Any idea? Coupling. Did we have coupling? We didn't make the decoupling. Filter. PI controller. PI controller. I mean, honestly, I can say that PI controller is somehow correct, but this is not exactly, because PI controller here is working well. So then one thing can be PI controller, but not 100% correct. Frequency. You're saying something. Frequency, voltage, active power, reactive power, PI. Yeah. What? It's correct. Tell me.
Maybe because of sudden change in load.
Well, we have also sudden change load here, but why we don't have that problem?
That is stable voltage. Maybe because of stable voltage.
I mean, I can actually accept your answer, but you don't know what you are saying. Yeah? So you mean that voltage is stable, but frequency is not stable?
Because active power is directly dependent on frequency.
Reactive power also dependent to the voltage. So why voltage is stable, frequency is not stable? Yeah.
So the active power is partially being supplied from grid.
Mm-hmm.
So when we are using the grid to supply the power,
Mm-hmm.
there is some amount of fluctuation while the reactive power is supplied from DC source.
Yeah, I mean what you're saying is correct, but this is not the answer of this fluctuation. I mean, why if these things happen, why the active power should have actually fluctuation? This is the reason. Response time. Who said? So why this response time is good, but that one is not good? Yeah. Inner control. Linear control. But we are using also PI controller here. I mean, one answer can be response time, because also we use the filter, and filter provide the delay, and then the PI controller cannot follow it. So if you look at this one, you see that we have a filter in D axis, but we don't have in Q axis. That one is providing actually this fluctuation. But there is another answer also for that one. Another reason. Inertia.
Also inductive behavior of the grid.
Yeah?
Sudden changes of the current is not supported in the grid.
Mm-hmm.
It has more energy.
I mean, basically, the reason is that when we are talking about the grid, then inertia is linked with the frequency, and frequency is linked with the active power. So for this reason, if you don't have very strong grid with high inertia, it cannot damp this part. So this part is coming from the impact of the filter, impact of PI controller, and lack of inertia, plus some part tuning also is important. Yeah, for the PI controller. So you got the answer, Darshida? So what is the reason? Inertia. Inertia, what is the weakness of inertia? Why inertia make this that much problem for us? Do you know? Inertia is not enough to support this.
Not enough to support.
Support what? Yeah. Okay. So it's not enough to support the fluctuation in the grid. Okay, so it cannot damp it. I mean, one is, if we have the strong grid, we cannot have that much. You see that it jumped from 10 to 15. So it means that beside the filter and the other things that make the delay, then it also provides somehow weakness from the grid which cannot damp it. And one thing, if we consider the impact, is here. Look, if you have this current from the, you see we have some notch here. Look at here, look at here, look at here. You see it? So if you get back to this one, you see they have some notch here. Okay? And the reason is that, do we have better? Yeah. Look at here. We have here. Okay? And the reason is that the PI controller follow the reference. So when the reference is changing, so when, for example, when we have this current, if you look at, we have the current like this. So the PI controller is expected to change, follow the reference current. So when it reach to here, then the direction of the reference current change. So it goes like this and then go like this. So this notch is happening because of this. And if you see here, you see when the direction change, look at here, when the direction change, so we have notch. It cannot follow very well. Udaya, do you have any idea? You can say, I agree with you. Yeah. No. Okay. Yeah, you see that one? Yeah, this one? We have, look, we have. But it's going to a steady state, so then it's not following the reference. But this is because of the delay that it makes it transient. Reactive power? Oh. Mm-hmm. Mm-hmm. Next one. So is not there because we don't have filter. So look at here. We don't have filter here, reactive power, but we have a filter here. Then it makes the delay. Then when it makes the delay, then PI controller follow the reference by the delay. So then it provides this fluctuation. Probably inertia is enough to damp the fluctuation, a small fluctuation, but the main is coming from the delay. Inertia and controller also. Yeah, tuning of the controller. How are you? You okay? Yeah. Sleepy? You want coffee, tea? No? Good. Okay. So why we have actually, why we don't have actually fluctuation here? When I look at the eyes of the student, I can understand the answer, okay? Darshita, why we don't have actually due to inertia? Inertia. You forget to say PI controller. Yeah, PI control, oil filter. Oh. Yeah, you say, yeah, like this one. One of them is answer. Okay. Okay, good. So now we see that if we have the nonlinear load, the reference that we have is very nonlinear. Actually, I draw here and said that it can be combination of the fundamental frequency and harmonic. So you can split these two parts to the DC and fundamental frequency. But you see that when we increase the, we connect the DG, it compensates all the linear active and reactive parts. But when we increase the load, we see that the part of the active and harmonic actually in active power can be compensated. But then we see that the load current and the converter current have the gap actually. There is this, and this distance is that fundamental frequency, this part. Okay, you see that it can compensate all the reactive, all the harmonic, and some part of the active power, but not all of them. So for this case, we have a gap bit. But here we see that before actually load increment, the maximum power injected from DG to the load is bigger than the load demand. So we can compensate all of them. But here we cannot compensate. But fundamental frequency partially is from the grid. But again, we see that the reactive power, all of them in even after load increment, we have also possibility to compensate it. And this is also power factor correction. We see that the active power and reactive power are in grid current and grid voltage are in phase. What is the meaning of in phase? Siddhant?
Phase means
Angle, yeah, okay. In phase, voltage and current are in phase. What is the message they are going to give? Tell me. Power factor is equal to unit value. It means that grid doesn't provide any reactive power. Okay? You are not listening to me, yeah? Give it your hand to me, like in this part. Okay, you know the Avicena, yeah? Avicena, actually, this doctor, is Ibn Sina or something like. He's the most famous. Udayat, do you know Ibn Sina? Avicena, yeah? You can explain to them who? The doctor actually. Yeah, I mean, someone went to, he was the most famous one in the world. And then the father said that, my son, actually when I talked with him, he's indifferent. And then he got the hand and said, okay, so said that Pakistan, Afghanistan, India, yeah, okay, change. Then said that, okay, Mumbai, Delhi, Hyderabad. Then said that, okay, no, Varangal, yes, okay, that one. Okay, so then said, okay, this is the Varangal. So then said that this street, that street, okay, said that, okay, that street, changed different, okay. Then said that, okay, the blue color door, no, white color door, no, red color door, oh, okay, I said, okay, your son is in love with the girl in Varangal, that street, that home, okay, so, so this is why you are always here, but your mind is flying somewhere else, okay, so, yeah. So the people are making joke with you, okay? So listen to me. I ask you, or bring Arya and then I leave you. Okay? Okay, good. So now we are talking about the THT. One important thing is that, you know, we said that we have a standard.
I'll bring in tomorrow.
Okay, okay. So, yeah. Okay, let's see. Tomorrow I'm not here. So, anyway, we talk about the actually THD, total harmonic distortion. So, you are familiar with the THD? Does anybody know? Probably, do you know what is the THD? So, THD means total harmonic distortion. So, when we are talking about THD, if we said that the equation is like this one. For example, THD of a current, THD, is IRMS minus IRMS in fundamental frequency to IRMS fundamental frequency in. Okay, so it means that if we increase actually the value of the THD, if we said that THD of this signal is 25%, it means that it has something like this. Now THD of this system is 22.97, so it has a harmonic. And if we increase the value of the THD, it means that it is more non-linear. So this is, for example, THD is 4.18%, but this is 22.97%. So it means that the system is too non-linear. So in grid code said that, I'm a little bit trying to ask him again that, do you know what is the grid code? So anyway, in a standard say that, you know, you are allowed to provide electricity for the grid with THD less than 5%. If the THD is more than 5%, you are not allowed to inject to power grid. So by this assumption, you see that, you know, when we have the load connected to the grid and the THD of the load is 22 or 23, anything, 22.97%, by this DG can compensate it, and then the grid current, the THD of the grid current go to 4%. So it is in the standard value. So it doesn't consider it as a pollution or a pollution that you cannot actually consider for the grid. So by this, we reduce the THD of the grid. Such a beautiful controller we have. We can actually compensate the reactive power. We can provide the active power. We can actually compensate the harmonic. Then the power factor of the grid is unit value. It means that we don't provide any reactive power from grid to load. And also THD of the system is less than 5%. It means that we have a very nice and high quality power from the grid side. Okay? All of these benefits are coming from the integration of this converter-based generator to the grid. So, now I'm going to conclude this chapter, and tomorrow, if you are, the next session, we will start to talk about operation and control of the converter-based synchronous generator. So, this gentleman, if you are interested, we will go through the inertia and how we can actually provide the model of the synchronous generator. In the control, we go one by one, start very basic, go a little bit modeling the system of the converter based on the synchronous generator, and then how we can provide the active power and reactive power like a synchronous generator to provide the stability of the grid and increase the efficiency, the strength of the grid by injection inertia to the grid. So we have different, but seems that we have too much fun next week. Yeah? Good. So, Udaya, I'm really tired. And sorry, I get tired, then I look for an excuse to reduce my stress, then talk with you. Okay? But we actually, yeah, we deal together later. Yeah.
Another 10 minutes. I do
10 minutes what?
Huh?
You're going to talk.
just general conversation. Fine, you can share. Laboratory also based on some MATLAB experimentation, those things that can be done from Monday or we'll initiate on Sunday. We'll see that whether it is going to happen next Monday, next week onwards. Anything that the students? Yeah, that's what we can, means like you do the things that what queries that you are having, that we will try to help you out to sort out your queries. Okay, and we will provide to the best. You know that the one thing is that if you give the flexibility for us, then the more content will be delivered according to our plans. Okay, and the if you want to have this kind of thing, that we can restrict. I mean, like anyway, it is part of the things that we will have the answer. I mean, like that here that I conveyed the professor that this is the tutorial. Means like he is not aware our terminal. Means like not that much hands-on. Means like don't you will form a group and will given some assignment for you, and you execute that assignment by using either software or means like it is a kind of analysis that you can do that. It is there, okay. But in the sessions also somewhat we are shuffling here and there, but to have the continuity of that session, we are trying to shuffle those things, but all the topics are going to be covered within the stipulated time period. Yes, yes, that will be there. We will give the things. Any other things? Yeah, actually we thought of provide means like anyway material will get it to you, either in the form of soft form or of hard form, that we'll see, but initially you take the soft form. Yeah, fine. And that you are knowing that due to some limitations and other GAN, so that you are at what's the kind, it is there in your place, the conduction courses we are trying to do all from our side to to be happy program. Okay. Yeah, fine. Any
So
still?
sending to your WhatsApp.
Okay. You are subgroup?
No. To your WhatsApp.
Yes, fine. I can share. Yes. Yes. Side. Okay. The thing. Other still.